Hello students. In this video lecture I am going to give an introduction to a multivariate tree. Before understanding the characteristics and the advantages of multivariate tree, let us first identify the drawback of the binary tree. Why we should move to a new type of tree. The binary tree as it grows may become very tall. The height of the binary tree can become very significant and leading to difficulty in managing such a very high height binary tree. So for example, if you construct a binary tree with 1,000 entries, it will have a minimum height of 10. Whereas if the tree is having 1 lakh entries, then its minimum height will become 17. So such a tree will become very difficult, and especially if it is unbalanced. So if you construct and try to maintain an unbalanced binary tree, it becomes a very difficult task. So in order to overcome that drawback, we are now going to build a new type of tree which is significantly different from a normal binary tree, and that is what we are referring as a multivariate tree. The first difference between a multivariate tree and a binary tree is that for a multivariate tree, the number of children for every node is not restricted to 2. Instead, it can have more than 2 children. So, which means that what we are discussing is not a binary tree, but it's a general tree. So, only for a binary tree, there is a limit that a node can have maximum of 2 children. So, for a multivariate tree, that is not imposed that as a result, any node can have more than 2 out degree or more than 2 children. That is first difference. Secondly, in any tree, whether it's binary tree or general tree, so far we have discussed that a single node will have only one data. So only one key value will be present in each and every node. But now in a multivariate tree, a single node can have multiple entries. So there can be more than one data represented in each node, which is a second difference between the multivariate tree and the remaining trees we have completed so far. So each node may have multiple subtrees. Since the number of entries in the node can be more than one, the number of subtrees will also increase accordingly. We will see the example to understand this. These structures, these type of MA structures are highly useful in a number of applications like internal search trees, spell checkers, external file indexes. So my MA search tree. So we are now going to focus on in the various aspects of MA search trees. So MA search tree is a alternate for binary search tree. So whenever we want to store large volume of data which needs to be searched frequently, so far we thought ABL tree is the best structure, but now MA tree is going to improve that further. So an MA search tree is a search tree in which each node can have more than 2 children, which we have already seen. But now it's also restricted. So though a node can have more than 2 children, it's not unlimited. It is limited to m. So m is nothing but the value that is assigned as the order value for a given MA tree. So for example, if you create a MA tree as by replacing m as 5, then it is called as a 5-way tree or 5-way search tree. So in such case, the maximum children a node can have is 5. So 5 defines the maximum number of children for a node, and it is also called as the order of the tree. A multivariate tree of order m is one in which a tree can have m children. That's what I was telling you. Next is, given a non-empty multivariate tree, we can identify the following properties. Property number 1, each node has got 0 to m subtrees. Property number 2, a node with k less than m subtrees contains k subtrees and k minus 1 data entries, which simply means that a node can have a maximum of m subtrees. The number of subtrees for a node is the maximum is m, but the number of entries in each node is restricted to m-1. You can see the difference. The number of values that can be present in a single node is m-1, but the number of children for a node is m. So it's 1 less than the number of values or number of entries is 1 less than the number of children. We will see the example. If you don't understand this, you don't need to bother. It will become clear as I show you the example. The key values in the first subtree are less than the key value in the first entry. The key values in the other subtrees are greater than or equal to the key value in the parent entry, which simply means that the MA subtree retains the characteristic of the binary search tree in this aspect. So the left subtree will be less than the parent, the right subtree will be greater than the parent. That's what is being said here. This is the third property of a MA search tree. Next, the keys of the data entries are ordered in ascending order. So key 1 less than or equal to key 2, and key 2 will be less than or equal to key 3, and so on. So these are the 4 properties of a MA tree. Let us just recall it again. Each node can have maximum of m subtrees or m branches, and but only m-1 entries. So the second point says that a node can have maximum of m-1 entries, and third point says that we have to build the MA search tree very much like a binary search tree, so that the left values are less than the parent, right values are greater than the parent. And the last characteristic is that within a single node all the entries have to be in ascending order, and all subtrees are themselves multivariates. This is the typical usual one. So this is how the MA tree is going to be constructed. So we will have multiple entries in each node. So we can see here that it's a single node, but we can have we have got 3 keys inside that particular node, and there is a left subtree and a right subtree for K1, which will be following the order that the keys are less than K1 and these keys are greater than K1. And similarly for K2, these keys will have to be less than K2, and these keys have to be greater than the value of the K2. So in this way we can construct a MA tree. Now this is the actual example we have got. So it's called as a 4-way search tree. So this is treated as a 4-way search tree. So when I say 4-way search tree, you have to immediately recognize the conditions. Number 1, a single node can have maximum of 4 children. A single node can have maximum of 4 children or 4 branches. Number 2, within a single node there can be maximum of 4 minus 1, that is 3 entries. Let us verify whether this particular tree qualifies for that. The number of children for this particular node is 4. Child 1, child 2, child 3 and child 4, which means that it does not violate the maximum limit. It's within that limit only, so it is verified. Secondly, the number of entries in each node has to be m-1, which is 4 minus 1. That is also maintained. So in none of the nodes this rule has been violated, and as a result this tree can be considered as a MA tree. And one more point is ascending order. So 50, 60, 80. So everywhere we can see the nodes are in having the values in ascending order, and the left subtree is less than the parent, whereas the right subtree is greater than the parent. Similarly for each value, the left is less than and the right is greater than the value. So it's a MA search tree. So that's what is being mentioned here. Each node has maximum m children and m-1 key fields. Each node, the keys in each node are in ascending order. Keys in the first I children are smaller than the parent, whereas keys in the last m-1 children are larger than the value. Now a few observations we could make is that number one, it's a binary search tree. So left children are greater than or less than the parent, right children are greater than the parent. So it's a basically a binary search tree. Number two, uh, the keys are greater than or equal to k1 and less than k2. It serves as rights. And one more thing is that see each except the first subtree, every subtree will act as both the left and right subtree. For example, for this particular subtree is the right subtree of 50. At the same time, it is the left subtree of 60. So it's serving the role of dual purpose as left as well as right subtree. In other words, whether a subtree is left or right depends upon from which node you are viewing it. If you view it from 50, then this is right subtree. Whereas if you look at it from 60, then it's a right subtree. It's a left subtree. And also note that there is one more subtree than there are entries in the node. There is a separate subtree at the beginning of each node. That is the same point that maximum children is up to m, but maximum values or maximum keys inside a node is m minus 1. The first subtree identifies all the subtrees that contains keys less than the first entry in the node. And because each node has a variable number of entries, we need some way to keep track of how many entries are currently in the node. You can see that there will be a problem when you implement this, because you don't have a fixed number of values in every node. So this node contains 3 entries, this contains 2, and this contains 1. So we have to somehow know that a particular node contains a certain number of values. So we can use and additionally a field called entry count. So this point is only relevant when you implement this MA tree through a program. One more example, this is also a four-way tree. Again we have to check the condition, whether the conditions are preserved. So four-way means maximum 4 children, 1 2 3 4, so it's valid, it is proper. Secondly, maximum 3 keys, so that is also not violated anywhere. And the next one is ascending order within each node, 50 100 150 85 95, so it's all in ascending order. And the last condition is left subtree less than parent, right subtree greater than parent, and that is also preserved. So this is a MA subtree of order 4. And if you want to represent this through a program, then the ideal data structure is said to be array. Okay, now we are actually getting into a modification of the MA tree, or in other words an improvement of a MA tree called B tree. So it is in fact the B tree that is widely used on a number of applications for the purpose of representing a huge volume of data, which facilitates quick searching. So B tree is very famous, and also it's very useful data structure to represent information. B tree is not totally different from MA tree. It retains all the characteristics and properties of the MA tree with some additional properties. So we just need to know the additional characteristics or restrictions added to a B tree over the MA tree. The MA tree has the potential to greatly reduce the height of a tree. However, it still has one major deficiency, that it is not balanced. So if you balance a MA tree, then it becomes a B tree. So that is what we are going to discuss next. But how this has been achieved, that the height is greatly reduced, is that because you can represent multiple values in each node. So if you implement if you represent the data through a normal binary search tree or even AVL tree, you can only have one value in each node. As a result, it will become the height will become huge. But now in the case of MA tree, you can have maximum of m minus 1 entries in each node, and as a result the height will get reduced. That's what the advantage of MA tree. but we are going to make it even better by balancing it. So that is what we are referring as a B tree. So a B tree is an MA search tree with the following additional properties. The root has at least two subtrees. So previously with the MA subtree, there is no limit on the minimum number of subtrees for a root. The root can have 0, 1 or 2 subtrees. But for a B tree, it can either have 0 subtrees or 2 subtrees. It can't have a single subtree. That is a restriction imposed additionally onto a B tree. Secondly, each non-root and non-leaf node have at most m non-empty children. That is the same restriction we have already come across, that a single node can have maximum of m children. And what is additionally added for a B tree is that the minimum is also limited to m by 2. So for a MA tree, only the maximum is said m. You can have maximum of m children for a node. But for B tree, in addition to that restriction, the minimum is fixed to be at least m by 2 non-empty children have to be there, and as a result it becomes half full. So this is second additional condition to be imposed for the B tree. And the third one is the number of keys in each non-root and non-leaf node is 1 less than the number of its non-empty children, which is the same old condition, that you can have m minus 1 values or keys in each node. All leaf nodes are at the same level. This is again a new condition, that all the leaf nodes have to be at the same level, and that is what makes it to be a perfectly balanced tree. So B tree is basically balanced tree, and it is in fact perfectly balanced because all the leaf nodes have to be at the same level. Otherwise it can't be considered as a B tree. And the last condition is that a leaf node has at least m by 2 minus 1 and at most m minus 1 entries. Remember that if for this condition is different for non-leaf nodes. So for all the non-leaf nodes, the maximum number of entries is m minus 1. That is that's just retained from the MA tree. So for every node, the maximum entries is restricted to m minus 1. But for the leaf node, it has to be at least m by 2 minus 1. So it is m by 2 minus 1 is additional condition. There is an additional restriction on the leaf node, that each leaf node has to have at least m by 2 minus 1 values, at most m minus 1 entries. This is common. M minus 1 is common for all the nodes, but m by 2 minus 1 is an additional restriction on the leaf node. So only if you construct a B tree with having all these characteristics, it can be considered as a B tree. B tree is perfectly balanced MA tree in which each node, with the possible exception of the root, is at least half full. And this type of tree will be used when the data to be accessed stored is located in secondary storage, because they allow for large amounts of data. So whenever we want to represent a large volume of data, especially secondary storage, because secondary storage is the largest storage in any computer, so we used to store huge volume of data in secondary storage. So in those cases, the B tree representation is generally used for representing the data, so that whenever a file is needed to be by the user, it can be easily located. The search time will be minimized when the B tree is used for the representation. So before proceeding to an example, for example, if you say that the order of a B tree is 3, then the minimum number of subtrees it must have is 2, because m by 2. These are all, you just have to memorize these conditions, that if the value of m is given, then the minimum number of subtrees have to be m by 2, maximum can be m. Similarly, the minimum number of entries in each node has to be m by 2 minus 1, whereas the maximum have to be m minus 1. So accordingly, you can calculate these values. So based on the order value, based on the value of the m, you have to calculate the remaining values and have to ensure that this is properly fulfilled by the given tree. Only then we can consider it as a valid MA tree. So let us check whether this particular tree is a B tree, whether it's a valid B tree. First thing is, the root have to have minimum 2 children. You can see that it has got 2 children. So the first rule is fulfilled. The root has got minimum of 2 subtrees. Number 1. Number 2, each node can have at most m children. M is 5 for the given example. So the maximum children permitted is is 5. Minimum is m by 2 minus m by 2. So minimum is m by 2. So that has been maintained. So you can see here that this particular node contains 5 children. This particular node contains 5 children, which is what is allowed, the maximum allowed for this level of tree. So that rule is also valid. Secondly, the number of values in each node have to be minimum m by 2. So minimum m by 2, which is nothing but 5 by 2, which is 2. So integer division results in 2. So this particular node fulfills that condition, and the root can have less than that. So that rule is not applicable for the root. Root can have single value, but except the root, all other nodes must have m by 2 number of children, and uh, maximum number of entries is m minus 1. So here you can see that it has got 4 entries, which means m minus 1. So that is also the maximum, and so everywhere you can see that the conditions are fulfilled, and so it seems to be a valid B tree. Let me just summarize the points again. So to prove that it is a valid tree, point number 1, the root is not a leaf and it has 2 subtrees. Rule 1 is verified. Secondly, the left internal node has the minimum number of subtrees, which is 3. So the minimum number of subtrees is 3 because m by the left internal node has the minimum number of subtrees 3, and the right internal node has the maximum number of subtrees. So because the condition is m by 2 minus 1, and that has been maintained by the nodes. The rule 2 is also verified. And thirdly, all the leaf nodes are at level 2. So all the leaf nodes have to be at the same level, and you can see that the leaves are all in the same level. Next one is 2 leaves all, okay, therefore the tree is a valid B tree. So because these conditions are fulfilled by the given B tree, it is said to be a valid one. And this is again a similar question. You have to check whether this given tree is a valid B tree. So it's a 4-way tree, which means that the maximum children allowed is 3. Maximum children allowed is actually 4, but only 3 children or subtrees are there with every node. So that is not an issue. Only maximum is 4, but it need not be there with the any of the children. So 3 is allowed. Secondly, the number of entries in each node have to be maximum m minus 1. So maximum m minus 1 means that 3 is the maximum, and you can see that this particular node contains the maximum of 3 entries, and other nodes contains 2 entries. That is also valid. So, and also left subtree less than the parent, right subtree greater than the parent, and all the leaf nodes are at the same level, and internally each node contains the entries in ascending order. So at all levels you can see that the tree fulfills the requirements of a B tree, and so we can conclude that this is a valid B tree. So with this I am concluding the first part of the discussion, that you should have understood what is a multivariate tree, what are the properties of a multivariate tree, and what is a B tree, what are the additional conditions to be satisfied to make a MA tree into a B tree, and how to verify whether a given tree is a B tree or not. And the next video lecture we are now going to discuss about how to insert and delete into a B tree. Thank you.